Hello and welcome to TidyX episode 101. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick. And TidyX is on Twitter, Tidy_explained. Tidy.explained@gmail.com is where you can drop us a line, or you can open up an issue on the GitHub repo, or you can like and subscribe at the bottom of that YouTube channel and drop your comments and questions down there. We've gotten a lot of nice positive feedback over the last few episodes, so we always appreciate that.
Love and hearing it.
If you appreciate what we're doing and you'd like to contribute, we do have a Patreon page, and we appreciate everybody that has contributed this far. We appreciate anybody that would like to contribute. We enjoy doing this, and if you feel like it helps you, that's really awesome.
Yeah, we really appreciate it. We, like you said, great comments down below. Continue. We like interacting with you all and getting the feedback. You guys clearly are enjoying this series. So we're going to look more at how we can do things like this. Leave comments on ideas that you have going on in the future. So that's a good segue into what we're talking about, which is on to the next type of distribution that we're using for Bayes models. So Patrick, do you want to take us through that as I go to share my screen?
Yep. So in episode 1 of this series, we talked a lot about distributions and sampling, and we talked about the binomial distribution for successes and failures and Bernoulli trials, basically. And then we talked about count data and Poisson distribution. And then we talked about the normal distribution, which is continuous variables from infinity to infinity. And today, last week we did binomial distribution. Today we're going to talk Poisson distribution, and more importantly, the gamma Poisson conjugate. So last week we did the beta binomial conjugate, where we used a beta prior and we updated the knowledge of our beta prior using some likelihood observations from the binomial distribution, successes and failures, and that got us a posterior distribution. Today we're going to do the exact same thing, this time with count type of data. Poisson distribution is a distribution that assigns probabilities to the number of occurrences observed. Usually that's in a fixed period of time. This distribution is a single parameter distribution. So most of the distributions we've been working with have had 2 parameters: number of successes and probability of success, mean and standard deviation. This time, we're going to be talking about a single parameter distribution with the parameter being lambda. And lambda represents the average number of occurrences in that fixed period of time, and it also represents the variance of the distribution. So lambda is really unique. It represents both the mean and the variance at the same time with the same number. And so as lambda increases, as with most of these things, the Poisson distribution begins to start to look more like a normal distribution. And so this also increases the spread and variance, since lambda represents that as well. Remember, single parameter distribution. And like most things, again, the normal distribution tends to fall into place in nature once we've seen a lot of observations. Okay, so let's put the Poisson distribution in place, or in action, before we get into the gamma.
Figure out how we think about this. What is the Poisson? It's got lambda. What does that mean?
Yeah, so we've got a basketball player named Sally, and on average, she scores 15 points per game. What is the probability that Sally would score 25 points per game in the next game? So writing this out in probability statement, we're saying, what's the probability of our data, given our hypothesis is a likelihood, it's an observation, it's a very frequentist way of looking at things. What's the probability that she scored 25 points, given that she only averages 15 points per game? So we set this up by saying lambda is our mean, points scored per game, 15. We're saying the number of points we observed or score is 25. How likely or unlikely would that be? We can do this by hand. That's the math right there that will get you to estimating this probability. I wrote it out by hand, so if you want to see it from first principles, you can. But it'll produce the exact same output that we can get from the dPoisson function in R. So in R produces a nice helper function. The only 2 arguments you have to pass it are the observations, and then we're looking at those observations relative to the lambda, relative to the mean and variance that we have within our data. Okay, cool. So same number, great, works out. We can look at this against a range of potential scoring outcomes. So let's say, what's the probability that she scores anywhere from 0 to 30 games, given what we know about her lambda, about her mean and variance. Again, just to be a bit cheeky, I did it by hand so you can see it if you wanted to mess with it. If not, we can always do the handy dandy little helper function, and this little plot down there is going to plot the exact same thing. This nice little stick histogram in base R. So there you can clearly see the highest amount of probability mass, because remember, we're dealing with discrete outcomes, 0, 1, 2, 3, nothing in between. The highest probability mass is right there, right around number 15, which we know is her average. Okay, so let's approach this as a problem statement. The average player on our basketball team, the average player for our population, is 15 points per game. And we just got a new player named Hannah, and Hannah is an absolutely devastating scorer. She's gone 22, 27, 25, 21, and 24 points each game over the past 5 games. And what we want to do is we don't want to get too crazy here and assume that maybe she's the next Sue Bird. But we want to take a step back, and we want to estimate Hannah's true scoring rate relative to what we know about the initial population. And scoring rate can be hypothesized to be any value from 0 to infinity. If we took a mean over a whole bunch of players, it doesn't have to be a discrete value like 13 or 17. It can be any of those values. It just can't be below 0. So we need a prior distribution that can represent a continuous probability distribution, a probability density function, and can take on any value from 0 to infinity. And so for that, enter the gamma prior. The gamma distribution is a 2-parameter distribution, and it represents continuous probabilities. And the 2 parameters are the shape parameter, or sometimes referred to as the alpha parameter, and that's the number of successes, and the rate parameter, or sometimes referred to as the beta parameter, and that's the number of observations. And this distribution can be used as a conjugate prior for the Poisson distribution. And the way in which we can determine the mean and the variance for the gamma distribution using those alpha and beta parameters is as such. These are the 2 little equations, and we're going to use those down below as we update our knowledge about Hannah based on the 5 observations given what we know about our population. So how are we going to find an alpha and beta that makes sense for our population average? We're going to use what's called moment matching. Last week, we didn't do this, but we referred back to episode 11 where we did do this. And if you go to episode 11, I wrote some functions that do moment matching for the binomial, for the beta distribution to find alpha and beta for the beta distribution, episode 11. This is how we're going to do it for the, exactly. This is how we're going to do it for the gamma distribution. So moment matching is a convenient way to obtain the parameters for a distribution. Just to refresh, we know the mean scoring rate for our team is 15 points per game, and we need to convert this into an alpha and beta parameter so that we have the necessary prior information to combine with our observations of Hannah's data. If we know the mean is 15, we could simply set the alpha and beta to have a relationship that represents this value, because we know mu is determined by dividing alpha, alpha divided by beta. We could set alpha and beta to 30 and 2, and that would give us a mean of 15, and it would give us a standard deviation of right around 3. An alternative approach is to use moment matching, or method of moments, and we're going to use that to help us determine what the appropriate alpha and beta parameters should be for a group of observations. So let's say that we've observed a whole bunch of scoring rate of the players in our league, and we've observed 150 players over several seasons. And so from those 150 players, we've observed that on average, they score 15 points per game with a standard deviation of 5. So now that we've simulated some fake data of 150 players of historic scoring outputs, when we run this, when we calculate our mean and our variance and our standard deviation, we get right around 15 and right around 5 as a standard deviation. Okay.
What we'd expect.
What we'd expect. So let's turn this into alpha and beta parameters for our gamma distribution, and we do it like this. The alpha is, we're going to take the mean, we're going to take that population average, we're going to square it, and we're going to divide by the variance. And for the beta parameter, we're going to take that mean, we're going to take that population average, and we're going to divide it by the population variance. So one is mean squared, the other is mean, both divided by the variance. So we knock those two things out, and we get an alpha parameter of 10.7, and we get a beta parameter of 0.72. And lo and behold, if we divide alpha by beta, we get right around 15. And if we take the square root of alpha divided by beta squared, we get around 4.5. It looks exactly like the data that we had
It's
before.
almost like it's arithmetic.
It is. And now we are ready to rock and roll here and combine some information. So we've got Hannah's data. We've seen 5 games. That's her scoring. And the length is just saying it's 5. So we've seen 5 games. Great.
Perfect.
All right. So how do we combine this information? Simple addition. We take our alpha prior and we add it to all of the sum of Hannah's points over that time. And we take our beta prior and we add it to the number of observations that we've seen. So remember, the alpha parameter, the shape parameter, is the number of successes, the number of points scored. The beta parameter, the rate parameter, is the number of outcomes, or the number of attempts, right?
Yeah.
So
observations.
Now let's do some math. Alpha posterior divided by beta posterior gives us the mean of 22.7 and a standard deviation of about 2. And we can use our Q gamma function to get the 95% credible interval for Hannah, which is going to put us right around, she's probably somewhere between a 19 to 27 point shooter. And we can make a nice little plot of this. So Ellis, you want to walk us through what we're plotting here?
Sure thing. So we're going to use R gamma to give us some random values given. So we're going to simulate 1,000 new values using those same alpha and beta parameters that we just calculated for Hannah. We're going to then calculate the density plot because we want a density, or we're going to produce a density plot using the density function. There we go. English is good. We're going to set the color to be green, the line weight to be 5, and then we're going to set the limits to be 0 and 0.2. It helps if I pull this over so that we can see this. So this is the
that's our population.
Excuse me, that's the population one. Now we're going to add Hannah onto it using the same sort of method, but now we're going to use her alpha and beta posteriors. And there we go. So we've got her in blue and the population in green, so we can see that she is probably a fair amount better.
And so now we can do some Bayesian updating. So let's say she plays the next 5 games and she doesn't perform as well. So maybe she was like the change of pace, the change of scenery, she became really, she just got fired out of a cannon. And then the next 5 games, other teams got hip to that and started playing her differently. We're going to watch those 5 games. We're going to use the posterior alpha and beta parameters from above and make them our new prior information, because we're going to carry that forward and update that knowledge about Hannah. We observe the next 5 games where she doesn't fare as well, except for one game, game number 4. So we want to get our successes and our observations of 5 games. And we're back to updating our posterior now. So we do the same thing. We sum up all of her games in those 5. We add it to the alpha plus beta. We get new posterior alpha and beta parameters, and that gives us a new mean and standard deviation. And now you can see that she's moved downward a little bit from that 22 points to now she's maybe about a 17-point shooter. And you can see that on the on the ceiling, she's probably about nearly 5 points better than average. And on the floor of her 95% credible interval, we might be thinking that she's probably right around average for our team. Yeah. And we can go ahead and now plot all this information so we can see what the Bayesian updating looked like. Ellis, you want to take us through the last one there? The first 2 are the exact same.
Sure thing. It's identical to what we did before, except now we're going to add one last line. This is going to be red, and this is using this final set of posterior values for alpha and beta, so we can look at how, now that we have a 10-game sample for Hannah, how do we think she's doing? And so as you can see, it's definitely pulled her down, but maybe we're not ready to lose faith.
Yep. So obviously you could do this after every game. You could do this after every 5 games. And those distributions are going to dance back and forth a little bit until they finally settle onto something that is specific to Hannah. The other thing is, notice the blue distribution has a bit more longer tails to it, right? It has a bit more distribution area under the curve. The red distribution is starting to get more narrow because we've seen 10 games there versus the blue distribution where we've seen 5 games. And as we see more games and we get up to like 50 games, it's going to get really narrow and peaked. And we're going to say this is probably the indication of who Hannah is as a shooter on our team.
So we now know who Hannah is much better than we did originally.
More confidence in
Yes.
in the data.
The likelihood that she'll be shooting around 17 or 18 as opposed to the 15 is much higher.
Yeah.
Cool. There you go. And that is how you can use the Poisson and Gamma distributions to look at a person's scoring.
Yeah. Yeah. And if you're interested in more on scoring rates, I just did a blog today on shrinkage and bays and 3-point scoring in NBA players. And I do method of moments there actually for the binomial distribution. So, yeah, but that's what we got. And next week, we'll probably be looking at the normal distribution.
Yep, looking at the last sort of distribution that we can use, and then we can go from there. If you have any ideas of things you want us to look at, please let us know. We love hearing from you all. Love the feedback that we've been getting, as we said earlier. And so with that, I guess we'll call it. Thank you all for joining us for episode 101, starting the next 100 episodes.
Wow.
As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick. At Tidy_explained is where the screencast lives on Twitter. Tidy.explained@gmail.com is where the screencast lives in Gmail. You can open up an issue on the GitHub repo. You can go onto that YouTube channel, like and subscribe, and drop us a comment down below. And as always, if you like what we're doing and you'd like to contribute to our work, the Patreon page is open, and we appreciate anything that you feel like giving.
Yes, thank you all so much, and keep on exploring your world.